So lesson 6.2 is another round with vectors, and this focuses on the dot products. So in 6.1, the multiplying we did was how to multiply in a scalar. So basically take a number, a single number out front, and to distribute it. Now, today we get to talk about how to multiply vectors. We're specifically talking about the dot product. And so you'll notice up there the dot product of vectors. So given vectors u that has components u1 and u2, and v which has components v1 and v2. Dot product, so u dot v, is u1 times v1 plus u2 times v2. So this right here is going to be used pretty much throughout our whole lesson. This is our dot product. Now, I will throw in, realize when you multiply vector u times vector v using a dot product, we're not going to get a vector as an answer. It's going to be a number. When we get that, it's just going to equal some number. So just kind of realize that we're not getting a vector answer when we multiply these. We're getting a number. Okay, a single solitary number. Now, the following properties are true of dot products given vectors u, v, and w with scalar c. Some very basic properties that you use in all other aspects of math. U dot v equals v dot u. So that's just saying it doesn't matter which order your vectors are in when you multiply. They're going to give you the same answer both ways. U dot u equals the absolute value of u squared. And we'll use that one. We'll talk about that one a little bit. But if you also think about it, it kind of makes sense there that when you multiply u dot u times u, you're going to get u squared, and it is going to be the absolute value of it. 3, 0 times u is going to be 0. 4, u times v plus w is the same as u times v plus u times w, so kind of a distributive property happening there. 5 is similar, just reversed. U plus v times w is u times w, v times w, so that's just the w's out back, but it can still distribute in. And 6, cu times v, remember c is a scalar, so it's just a number, u and v being vectors. So the idea here is that c can really be multiplied in anywhere. You could do c times u, and then do the dot product between u and v. You could do c times v, and then do the dot product between u and cv. Or you could do the dot product u times v, and then multiply by c. So a scalar could be multiplied in any of those steps. But you would only multiply it in once. You don't multiply it times u and times v. Okay, so those are some of the different properties we're going to use today. Now, let's start in example 1 with practicing the dot product. And I think, so they weren't at the bottom of the page. I have them on the next page, yeah. Okay, so find each dot product. 3, 4, and 5, 2 are the vectors we're multiplying. And keep in mind, the hint I'm going to give you here is that if these are vectors u and v, then keep in mind this is u1, u2, and v1, v2. So kind of think of them as being in that form. I don't necessarily know if you need to write that out or not, but. And then remember when we're doing the dot product, I'm going to rewrite it since you can't see the top of my screen. U dot v is u1 v1 plus u2 v2. So what am I multiplying here? u1 v1 are going to be what numbers? Three and 5, thank you. So it's going to be 3 times 5 plus u2 v2. u2 v2 are going to be second number in each vector, so 4 times 2. Okay. Typical math. We've got to do our multiplying before we do our adding, right? PEMDAS, Aunt Sally, all still applies, of course. 3 times 5 is 15. 4 times 2 is 8. And 15 plus 8 is 23. Easy enough? Okay, let's practice with B. 1 negative 2 times negative 4, 3. What am I doing? Yeah, tell me besides just write it down, please. Okay. Doing 1 times negative 4 as our first components, plus negative 2 times 3 as our second components. 1 times negative 4 is negative 4. Negative 2 times 3 is negative 6. Negative 4 plus negative 6 is negative 10. Okay, C. C's in a different form, isn't it? So C is written as linear combinations. However, we know the component forms of those, right? And that's all you have to think about. So if it's 2i minus j, what would be the component form of 2i minus j?
2 negative 1?
Right, 2 negative 1. It's just taking the coefficients there, right? The coefficient of I is 2, the coefficient of j is negative 1. 3i minus 5j is going to have coefficients of 3 and negative 5. And I'm not saying you had to rewrite them out in component form. You didn't necessarily need that visual, but making sure we're all tracking here. So U1, V1, my first components. 2 times 3 plus U2, V2. Negative 1 times negative 5. 2 times 3 is 6. Negative 1 times negative 5 is 5. And 6 plus 5 is 11. Okay, so when you see this multiplying, you see that multiplication dot, this is what you have to think. You have to think dot product here. Luckily, it's not difficult, though, is it? Okay, look at example 2. It's telling us to use the dot product. So they do want us to use the dot product to find the length of the given vector. So use the dot product somehow, and we want the length of the vector. Thoughts on how we could do that? Yeah.
It's the length of magnitude.
It is. Length is magnitude. Huh? Look up at it. I'm going back to my first screen. It's just the top of your notes. What property?
Can we do 2?
Yeah. Does property 2 make sense? And here's, property 2, what do you notice? There's absolute value, right? So that's magnitude, which is also length. So basically you were looking for the property there. So the idea that u times u is absolute value of u squared. So this is property number 2 from above. And property number 2 from above says that the absolute value of u squared is equal to u dot u, u times u, right? Now what is it we're really trying to find here? When we want to find the length, the magnitude, are we trying to find the absolute value of u squared? We don't want the absolute value of u squared, we just want to find the absolute value of u. So before I start working, and you can wait and do it later as well too, but what do I do to make this the equation I need it to be? Right now it's absolute value of u squared. I really only need to find absolute value, so mathematically we can do what to both sides of the equation? Take the, how do we get rid of that squared? Square root. If you square root one side, you can square root the other side. And so the equation we're actually going to use, the absolute value of u is equal to the square root of u times u. Okay, so that's the formula we're going to use. What is u? Absolute value of u is equal to the square root of u times u, so we're doing 4 negative 3 times 4 negative 3. How do we multiply the vectors 4 negative 3 and 4 negative 3? We're going to use the dot product again, right? So if we use the dot product here, square root of what? What am I multiplying here? First times first, plus second times second. Do the math. 4 times 4 is 16, plus negative 3 times negative 3 is 9. 16 plus 9 is 25, and the square root of 25 is 5. So we just found the absolute value of u to be 5, or in other words, the magnitude or length of the vector to be 5. Okay, so it's using that property too. You are always, you are welcome to just kind of realize, okay, right here, that's always going to be a formula that you can use, so to speak. And the fact that you're doing the absolute value of u is the square root of u times u. Okay. Questions on dot product? Pretty easy. We're not done with dot product, but we're going to mix in some other things. So now we've got to talk about an angle. And what we're looking at is a formula that can help us find the angle between two vectors. So if theta is the angle between the non-zero vectors u and v, then the cosine of theta is equal to u dot v over absolute value of u times absolute value of v. Okay? So this is a formula we're going to be using. And we're going to use this formula. Yeah, you just lay on my desk. Thank you. We're going to use this formula to find theta. Now, picture-wise, theta is the angle between the non-zero vectors u and v. All that's saying is if I have vector u and I have vector v, then theta is the angle between them. Okay? That's all we're talking about. That's our relationship between u, v, and theta. Okay? So, example 3. Find the angle between the vectors u and v. Well, hey, guess what? We have a formula, right? We're trying to find the vectors, or the angle between the vectors u and v. We're trying to find theta, of course. And our equation is this right here. So let's fill it in. We're going to be doing cosine theta equals, and on top it's going to be u times v. So I'm going to go ahead and write that out longhand for right now in that it's vector 2, 3 times vector -2, 5 over the absolute value of u. So the absolute value of vector 2, 3 times the absolute value of vector -2, 5. And that right now is really just me filling in the given information. Now, let's see. Let's do a little bit of the math here. I'm going to leave it as cosine of theta for right now. Okay. How do I multiply the vectors 2, 3 and -2, 5? What do we do here? Dot product, right? This is what we learned up at the top part of the page. And so dot product, in order to multiply two vectors, says we're going to be doing first times first plus second times second. So again, I'm writing it out. 2 times -2 plus 3 times 5. And if I go ahead and put that, go ahead and carry that over. 2 times -2 plus 3 times 5. What is that? -4 plus 15, so that's going to be 11. Okay, so numerator of 11. Denominator. How do I do the absolute value of the vector 2, 3? Absolute value is the same as doing our magnitude or length. So in order to find the length or magnitude of this vector, you're doing the square root of 2 squared plus 3 squared. Square root of 2 squared plus 3 squared. 4 plus 9, 13. So that's going to be a square root of 13, if you will. So may I have done my math wrong? Okay. Second one. How to do the absolute value of -2, 5? Same thing, right? We're doing that magnitude or length, so it's going to be square root of -2 squared plus 5 squared. -2 squared is 4. 5 squared is 25. 4 and 5 is 29. So square root of 29. Now, realize what we have here, folks. We're not done. Because this originally was what? This is cosine theta. We did all this stuff, all this big fancy stuff in this big fraction. Cosine theta equals what? Cosine theta equals that fraction, 11 over square root of 13 and square root of 29. My job is to find theta. How do I find theta at this point?
Cosine inverse.
Yeah, cosine inverse. If it's cosine theta equals a number, a value, then in order to find theta, we're going to do cosine inverse of this fun little fraction, 11 over square root, and it's square root of 13 times square root of 29. Realize we can multiply those, yes? So I could rewrite this as square root of 13 times 29 if you want. And then at that point, it is definitely a calculator thing. So I definitely encourage you to try it on the calculators, as always. Always better to find the mistakes here than at home. So if you just want to put 13 and 29 in the same radical, that's what makes best sense to me. What are we getting?
55.5.
Yep, 55.49147701, but rounds to 55.5. 55.5 what? It's an angle, so degrees. Okay, so that is our theta. Oh, wait. Now, I want to talk real quick about, does this make sense? And so, let's see, I'm going to make it happen here. If I sketch a little graph here, think about the vector 2, 3. So, right 2, up 3. The vector 2, 3 does something like that, right? This is a hand-drawn sketch, not exactly perfect, but negative 2, 5 goes left 2 and up 5. Now, what did we just find? We just found theta, which is the angle between these two. Does that make sense right there, that that might be 55.5 degrees? I mean, in my brain, it fits the mold of it's an angle bigger than 0 and less than 90. So, I would say yeah. Okay, so there's the visual of what we just found. That's what I wanted you to see there. Okay, questions there? Yes.
So what do you do with these? Like, what's the purpose of them?
It's more used along in physics. You know, I mean, obviously, you know, going into physics, you would see this more. I'm trying to think. I mean, places where we're talking angles and whatnot would be the places that we would go with this. I definitely don't have any good examples off the top of my head. But, you know, something that uses more along the physics direction is where you would be going with this. Okay. I mean, for us, it's an introduction right here. I mean, that's all it is. I'm not going real deep into this by any means. Okay. It's just more of a little bit of an introduction, but it falls into the trig category of our standards. So, okay. In fact, we have a whole, you'll notice these standards, I think they're what? TR.V. We have a handful, those TR.V is my trig vector standards. We have a whole grouping of vector standards, so. Okay. Think you can do B? You've seen the process, right? We want the angle between the two vectors, U and V. So, can I skip how I set up the first step last time? That was more of an introduction type step. But I would say go ahead and jump into it. In order to do this, on top we're doing U dot V. U dot V says I'm multiplying U and V, and in order to multiply vectors U and vectors V, we use the dot product. Dot product says first times first plus second times second. Okay. If you go ahead and do the math there, what? -2 plus -3, so -5. Denominator says magnitude of U times magnitude of V. So magnitude of u, square root of 2 squared plus 1 squared. So that's 4 plus 1. So that piece is square root of 5 times magnitude of v. So that's going to be the square root of negative 1 squared plus negative 3 squared. 1 plus 9 is 10. So square root of 10. If you want, you can think of that as square root of 50 in the denominator, yes. So if I have cosine theta equals this fraction, how do I find theta? You find theta by doing the cosine inverse, right? Remember, theta will switch your input and your output. And so we're going to be doing cosine inverse of negative 5 over square root of, what if I say 50? Can you guys handle that? Okay, square root of 5 times square root of 10 is square root of 50. You can leave it as 2 separate square roots, it's fine. Just know how to use your calculator. And no, you don't need to simplify that square root. Nor do you need to rationalize because we're getting ready to put it in the calculator. Yeah.
135.
That's what my notes say. So what the rest of you are getting? 135 degrees. Did you check a visual out? Does it make sense? If you look at the vector 2, 1, that's that vector right there. If you look at the vector negative 1, negative 3, so that is left 1, down 3. Angle between them. And we're going for the less than 180 type angle here. Okay. Does that look like that could be 135? Again, I broadly classify it into it's definitely more than a 90-degree angle. It's definitely less than 180 degrees. Okay, it's the angle between the two vectors. And the angle between the two vectors is always going to be, I don't know what the word is. An acute or obtuse angle. It's not going to go more than obtuse. I don't know what that's called when it goes past 180. I don't know the wording there. Did you have a question?
Yeah, so basically if it says, since it could go either way, when it says between, it's always less than 180 if it's between.
Right, yeah. And there's a word for,
Really?
I don't know. At least I assume there's a word. I don't even know if I know it. For, you know, if you were to swing the other way and go past 180. But I don't know. And cosine inverse isn't going to find that, you know, angle. Because cosine inverse is going to find the angle between 0 and 180, right? Because remember, our cosine inverse output can only be first and second quadrant. So it's going to find the angle between 0 and 180. Okay? Not too bad, is it? You have to do the math and keep the math all straight, but as long as you can use your formulas, you should be good. Okay, before we move on to the backside, we have a vocabulary word here. And that vocabulary word is orthogonal. Vectors are considered orthogonal, which basically when you talk about what orthogonal means, it's basically about the same meaning as perpendicular, which what is perpendicular? What's a perpendicular angle? Or two lines meet that are perpendicular meet at a right angle, right? So when we talk about vectors that are considered orthogonal, which has almost the same meaning as perpendicular, if you look up orthogonal, it talks about having to do with a right angle. Their dot products equal 0. Okay? Dot products equal 0. So vectors that are considered orthogonal, in other words, we're talking right angles here. So vectors that meet at right angles have a dot product of 0. And the exception there is except with the 0 vector. I will mention that. So we're going to use that concept when we turn to the next page here. Vectors are orthogonal. Their dot product is 0. So, example 4, the top of the next page. Prove that the vectors u and v are orthogonal. What do you think? How are we going to prove that these two vectors are orthogonal? What did we just talk about on the previous page?
Your dot products.
They're orthogonal, their dot product is 0. So what should we find here to prove that these are orthogonal? We should find the dot product and find out if it is 0. So, here we go. U dot v. Product of the first two plus product of the last two. So 2 times negative 6 plus 3 times 4. Well, what's happening here? Negative 12 plus 12, which is, surprise, surprise, 0. I know, shocker here, isn't it? Okay, so did we prove that they are orthogonal? Yes. Now, I'm going to do another quick visual. If we look at these vectors real quick, I just want to see, does it make sense to you? So, right 2, up 3, puts one of my vectors here. And of course, this is hand-drawn, so it's not going to be perfect. Left 6, up 4. Left 6, up 4. Well, if you turn and twist your head the right way, does it look like a right angle? You know, I feel like I sometimes have to turn my head to make it make sense. Like, oh, okay, yeah. That looks like that could be a right angle, doesn't it? And that's even hand-drawn. That's not even official, you know. That's drawn with human error mixed in. Okay. Questions there? Okay, one more topic, and that is vector projection. Now, I do not have my typos fixed here, do I? I do not. Just slight typo here. So, a vector is projected onto another vector by dropping a perpendicular vector from one vector to the other. That's a lot of use of the word vector in one sentence, but to find the projection of u onto v, use the formula, and this formula should say, let me rewrite, projection, and since it's u onto v, u should be the big variable and v is the subscript. You have to be very careful because these cursive or italics U's and V's are hard to tell the difference between, aren't they? So, this is us talking about projecting vector u onto V. Let's see. I'm going to come up here because I have some empty space. I like empty space. And so I'm going to try and give you an idea of what I mean here. So if I have, we're going to call that vector V. And I'm going to call that vector U. Okay? And so the idea is if I am projecting U onto V, it's dropping a perpendicular vector from one vector to the other. And so the idea here is dropping a perpendicular vector. So a perpendicular vector right here. There's my perpendicular line. And the idea then, the projected vector is right there. Okay, that projected vector is U dropping on to V. And this is often referred to as U1, because it's kind of like a copy of U. A copy of vector U, that is. Okay, so that's the idea when we're talking about vector projection. That's the physical picture of what we're going to be doing here in example 5. Now, example 5, find the vector projection of U onto V. Then write U as the sum of two orthogonal vectors, one of which is the projection. Now, we're going to do this in 2 pieces because we've got 2 totally different things happening here. Well, not totally different. Make it sound like they're not related. They are related. So, vector projection. Find the vector projection of U onto V, which means basically we're trying to find, if this is U onto V, we're trying to find U1. And so I'm going to call this U1. And I'm going to write out our formula. It is the projection of U onto V. And we're doing the projection of U onto V. It's what was up above, which is dot product UV over absolute value V squared times vector V. So we're using that formula from up above, and that's all I'm writing out right there. Okay. Can we go ahead and fill in the math here? On top, do we know how to do U dot V now? That's the one thing you're going to walk out here with today, minimum, right? U dot V. So first times the first plus second times the second. 6 times 5 plus 2 times negative 5. And I think I'll come back and do that math here in a moment. Now, denominator. Absolute value of V squared. Well, absolute value, that's us doing the length, magnitude, right? So, but it's squared, which means I'm going to do the square root. I'm going to do my magnitude, the square root of V. So I'm going to say square root of 5 squared plus negative 5 squared. But then it says to take the magnitude and square it. So I'm going to be doing the square root and squaring it. So that right there is the fraction in front. And what I'm going to do for them, I don't want to get too much in here. That's going to be multiplied by vector V. I'll come back and multiply by vector V here in a moment, once I get that fraction mess situated a little bit better. So when I do this, oops, I don't need that long. Looking at what's happening in my fraction. 6 times 5 plus 2 times negative 5, 30 plus negative 10, so you got 20 on top. Denominator. 5 squared is 25. Negative 5 squared is 25. 25 plus 25 is 50. It's the square root of 50 squared. The square root of 50 squared is 50. So we have 20 over 50 times vector v. What do you know about 20 over 50? It's equal to 2/5. So what we're doing here is 2/5 times, what is vector v? Vector v was given as 5, negative 5. And so this isn't dot product now, is it? This is just taking a scalar, a constant, 2/5, and multiplying it in. 2 over 5 times 5 is going to be 2. 2 over 5 times negative 5. 5's cancel, but there's still a negative, so negative 2. So that right there is my vector projection. Now, that's U1. Technically, we have one other part to do that we're out of time for. So I will have to talk about that tomorrow. The part we haven't done is writing U as a sum of two orthogonal vectors, one of which is the projection. So I will talk about that tomorrow. I think this just affects 2 homework problems. So yes, do your homework. I will finish this problem, let you guys work on that. We'll check homework. So yes, plan on homework being due tomorrow. Got it?